Hello and welcome back. In this video, we are going to look at how to perform a logistic regression in TensorFlow. And for this, here is the link for the tutorial that's in the docs, and I'll be simply copying the code, but we'll be talking through the lines of code as we go through. And the data set that we'll be using in this particular uh, exercise is the breast cancer data set. So as usual, the very first step we have is setting up this workspace. So we'll need to import the libraries, and let's do that. Setup. So first we'll import TensorFlow, import TensorFlow as TF, then import pandas as PD, import matplotlib.pyplot as PLT, import Seaborn as SNS. If you do not have Seaborn already installed, you can install it by simply typing exclamation mark pip install dash q Seaborn, and this should install Seaborn uh, right away. After this, so the first is TensorFlow, then we have pandas, and then these are for visualization. And in addition to this, we are going to import some scikit-learn libraries. So import sklearn.matrix as here, just to stay in tune with what's in the docs, we are going to use the same alias, which is sk_matrix. And then we are also going to import temp file, and in addition import OS. So these are all the libraries we need, so we'll import those. And the Seaborn is installed, so I'm going to just comment that out. Next, what we need is, what we'll do is set the figure sizes, and for set figure sizes, so matplotlib dot rc params, and within square brackets we are going to specify figure dot fig size, and this is going to be is equal to 9,6. That's the fig size, and yeah, so that should work. Matplotlib is not defined. Matplotlib. Okay, so let's try this other way around. From matplotlib dot pib import pyplot as plt, run that, and then we have the matplotlib dot pyplot. So we also need to import matplot. So import matplotlib. Now this should work. Following this, we can say check the TensorFlow version. So TensorFlow version, and for this we can type print tf dot underscore underscore version underscore underscore, and we see that this is on 2.11.0. And finally we can set the random seed to get a reproducible results, and we'll set tf.random.set underscore seed is, and we'll use the same number that's in the docs, 22, so that we get the same output that's in the docs. Now let's go ahead and load the data set. So load the data, and here we are going to use the Wisconsin breast cancer dataset, and for that here is the URL. URL is equal to https :/archive.ics.uci.edu /ml machine learning databases / breast cancer Wisconsin wdbc.data. So that's the URL, and features that are in this data set are as follows. Features is equal to have a radius, then we have texture, perimeter, so all the dimensions, area, smoothness, compactness, concavity, then we have concave underscore point points. Wonder if that's a spelling mistake or that's just a column name there. Symmetry, and finally fractal dimension. With all these features, we are now going to add additional column names. Column underscore names is equal to ID diagnosis, and then we are going to write a for loop to append the column names, to append the features to these column names. For attr in mean ste largest, for feature in features column underscore names dot append feature plus underscore plus attr. So we are creating a new set of column names, and when we look at the column names after both these loops are run, column names, feature, let's see, that should be feature without an S. Okay, so these are the column names that we have created, and these are the ones that will assign to the data set. So let's get the data set using pandas read.cc. So get or read the CSV file that's at the URL. The data set is equal to pd.read underscore CSV URL comma names is equal to column underscore names. And now because we now have a data frame, we can simply say data set dot shape, and we should get the shape of the data set. That's the data frame we have, and we can look at the first few rows of that data set by typing our data set dot head, and here is the data set we have, and looks like there is something uh, not quite right, because we have these and then I wonder what these are. So we have the gender, looks like we have gender, and there are a whole bunch of other columns that do not have any column names. ID, so this should be the ID. Okay. Here's what we can do is I'm going to go to the UCI machine learning repository and in this browser and look at what values we have. So let's go here, and that's the folder, and here is the data set information. We have the instances, groups, attributes. So sample code ID number, clump thickness, uniformity, cell size, shape. So there are 11 of these along with the class in there, and what we have are 20. So we have the ID. This definitely is not the ID, so something is wrong. Let me go back and figure out what is exactly going on, and we'll come back and update this. Welcome back. So here I'm not sure what exactly happened. I reran the all these lines of code and they seem to be working fine. So that's the URL. These are the features, column names. This is the for loop, and then we are reading the CSV file, and we do have the all the columns in here along with the column names. Next, what we can do is look at another set of information by typing .info, dataset.info, open close parenthesis, and here we see that how many non-null values we have and what is the type of data in each other. So most of, so I think almost all of them are numeric except for this diagnosis column, which is abbreviated. So dataset and diagnosis, and here if we look at dot unique, it will tell us how many unique values we have, and there is M or B. I think this is malignant or benign, that those two values in there. Next, we can also create a train data set now from, so we can split this into train and test set. Let's create a heading here. Split data set data into train and test set, and for that, train underscore data set is equal to data set dot sample fraction is equal to 0.75. That fraction is going to go in the train set. Random underscore state is equal to 1, and so we can print length of the train data set, and after this, so that's going to be the train data set, and likewise we have the test data set, test underscore data set, which is going to be equal to data set dot drop, and we are going to drop the row, the indices from the data set which are in the train data set. So the train underscore data set dot index, and here we say length of the test data set, and we should see number. So you have 142 plus 427, and that gives us total of 569, and those are the number of records 569 that we have in the data set. Now we can so we need to separate the the target from the features, and for that what we can do is we'll perform this separation here. So, and additionally we need to drop the ID column because the ID column is not of much use. So we say drop the ID column, and the second thing we need to do is separate the features and the target. So x underscore train, y underscore train is equal to train underscore data set dot iloc, and we are going to get all the rows and the columns starting from index 0 up to the end, and comma train underscore data set dot iloc, and in this case we are going to again get all the rows and the column at index number 1. So if we look at train underscore data set dot head with open close parenthesis, here's what we are trying to do here. We are saying that we want the columns from this all the way to the end in the X train, and then we need this column at index 1, that's the diagnosis column, in Y train. That would be our target labels. And likewise, we are going to create the set for the X test and Y test, So let's type that here, X test. So I'm going to simply change this to test instead of train. And then we have this is test dataset, and then we have this is the test dataset. The X test, Y test, test dataset.ilog, and then this is this test dataset.ilog, and then we have this. Now when we run this, we have two nicely separated sets. So X underscore test dot shape, and we can look at Y underscore test dot shape, and likewise we can look at the train values for the train part of it. So X underscore train dot shape, and we look at the Y underscore train dot shape. And so we have the 427 427 and 142 142, and again the total records total columns we had was 32. We dropped the ID column, we don't care about that in this analysis. So 31, and out of 31 we separate out 1 for the Y and the rest of 30 for the X's. So we have 30 plus 1 31. Now it's time to pre-process the data. So let's create a heading for pre-processing the data. Pre-process the data, and here we are going to again convert, kind of one hot encode the values of B and M that's in the diagnosis column that is now a part of this Y values. So this Y value is just going to be a series of characters B and M, which we need to convert to numeric values. And to do that, here's what we are going to do is Y underscore train comma Y underscore test is equal to Y underscore train dot map. What map does is it'll we input a dictionary for this, and so there's two things we'll do: Y underscore train dot map, and then we do Y underscore test dot map. And inside of this, all we need to do is provide a dictionary of the old and new values. So the old value is B, that's the existing value, and we want to replace it with a 0. And so that's that. And then M, we want to replace that with a 1. Now, why are we assigning 0 to B and why are we assigning 1 to M? That is arbitrary, and for some, the general convention is that uh, anything that you are trying to uh, kind of look for as a positive is flagged as 1 and the rest is flagged as 0. So here we are interested in finding if the cancer is malignant, that is it is bad for a patient to have that type of cancer. In those cases we want to flag that as 1, the rest benign is flagged as 0. So this way we have we are with dot map we are applying this change to all the values in the series Y train and Y test, and then we're putting that back in those variables. Next, what we are going to do is we are going to convert the X train that's now a data frame to a tensor. So let's say we have a data frame. So let's call this df is equal to pd dot data frame, and here we have, let's say, just a one column. I'm digressing here, but just an example I wanted to show. This is the data frame we have, and which looks like this. When we use the TensorFlow, we can convert it to, so let's get df tf, let's call this df tf is equal to tf dot convert underscore to underscore tensor, and here we specified the df as the input, and we can specify data type if we wanted to, but we'll just leave it at that. And then we can look at the print type of df tf, and then we look at df tf, and here is what we get in the output. We have now converted this data frame to an eager tensor, and these are the values in it. So that's the idea right now, is to convert the X train and Y train to these tensors. So X train Y train is equal to tf.convert to tensor, and that's for one, that's for the x train, and we need to repeat the exact same thing for the y train. So I've copied and pasted 2 times. X underscore train, and this data type is going to be tf.float 32. Likewise, if we go all the way to the end of this, here we need to write y underscore train, and in this case with the y values we again can specify these data type as tf.float float 32, and then copy entire line. We remove this comma, don't need that, and paste it here. And the only difference now is going to be replacing all the train values by the test values. So let's change the test here and change the test there, and again we need to change the values for x train to x test, y train to y test, and hopefully this should work, and we should get, so okay, so we do have now the values converted, data frames converted to eager tensors. So we might as well write an heading here. So convert data frame to a eager tensor, or just say tensor. And here what we did was we one hot encoded, so one, or we can say convert characters to numeric values. Now we can look our the values x underscore train. This is how our data looks like now. It's the tensor, and likewise if we look at the y values, these are how our y values look like. With this information, we can now use it to uh, create a pair plot using the Seaborn library. And for that, we are going to use the data frame. So let's do that. sns.pairplot train underscore dataset dot iloc, and here we need all the rows from columns at index 1 through 6, and we have hue, so here 6 1 through 6, and then hue is going to be diagnosis, the column diagnosis, which has the values b and m, and diag kind, so how do we want our histograms to be plotted, and here we'll specify it should be a KDE plot. And so let's run this, and we should see a nice pair plot where we can kind of look and see how the features are related. So here is a nice plot where we can see that first of all the distribution of the values. So this is for the radius, and we can see the distribution of the radius for the red color. Red is the benign, M is the malignant, and we can see that the radius of the malignant tumors is looks like it's a bit larger than those that are benign. Most of the benign tumors have a smaller radius. And likewise, if you look at the perimeter, so perimeter again is larger, of course, larger radius, larger perimeter, and therefore larger area for the malignant tumors. At the same time, we would expect that if the radius is more, the area is going to be more, and that's kind of indicative of this line going up here. And if we look at these cluster of points for the texture mean, and we see two clusters are very well kind of separated, the orange and blue, and that's the objective that we have. So kind of trying to identify what should be the uh, kind of plane that we want to separate these into different classes. So with that, with that visualization, let's move on to the next step, where we are going to look at the uh, descriptive statistics of the dataset. So trained dataset dot describe, and here if we look at the values, we get this type of summary: count, mean, standard deviation, minimum, maximum, and the quartiles for each of these numeric columns. We can do a transpose on this, so we can say transpose, and so when we perform a transpose, we get the uh, transpose with the n. We get the descriptive statistics as columns, and then we have the rest of the values. If you want to just look at just the 10 of these records, we can do that by typing just :10, and here are the values. We have the mean, standard deviation, etc. for um, each of these features. The radius is, mean radius is this, and then we have the minimum value is that, then corresponding maximum value will be on the right hand side here, which is this. Okay, so now we'll do a step called normalization that we have seen earlier in one of the videos. Normalization, and for this we are going to write a class normalize with a method norm that will perform the normalization by zero mean data and dividing by standard deviation, and likewise unnorm, which will do exactly the opposite. So we'll create a class normalize, and this takes in tf.Module. That's the standard way, as we have seen earlier in this series, to inherit the properties from tf.Module. And the first we define the init, and inside of here we'll specify self and x, and then self.mean is equal to tf.variable tf.math.reduce underscore mean, x axis is equal to 0. Then we have self.standard deviation is equal to tf.variable and then tf.math.reduce standard deviation, again x comma axis is equal to 0. So that's the first part. And then the next what we need is the norm. So def norm, this takes in self and x, and then here we simply return the normalized input. So the normalized input is going to be x, each value subtracted by the mean value for that column divided by the standard deviation of that column. And so this is what is normalize the input, and this is, and here what we are saying is initialize the mean and standard deviation for normalization. Like the norm, we can also create another method here, unnorm, and this again takes in self and x, and here we are going to do the exact opposite. That is, we are going to multiply each of the values by self.standardize standard deviation, and then add the mean to this, the self.mean. So that's the class we have created, and here we can now call that class norm underscore x is equal to normalize, and we input the value of x train, and we can now use this norm x to perform the normalization. So x underscore train underscore norm, then x underscore test underscore norm is equal to norm underscore x dot norm x underscore train, and then norm underscore x dot norm x underscore test, and this is what we have. we we create these values where we have the xtrain, xtest written for uh, for the norm. And so if we look at the xtrain underscore norm values now, these are the normalized values. If we compare them with the xtrain, the original values without normalization, these are the values we have. And so you can see that these are mostly floating point numbers and there are no large values in there as compared to the values up here. Okay, so with this normalization step done, we are now ready to look at the logistic regression itself. So let's do that. And we won't go into the details of what logistic regression is and the equations behind it. I suggest you could check out the intermediate series, or you could check out the docs that is at the link at the beginning of this particular notebook. But what we'll do is we'll first in logistic regression we'll try to create the sigmoid function that we need to use. So create so there should be a comment, create or visualize the sigmoid function. And for this we have the x is equal to tf.linspace minus 10 to 10, and we have 100 values, 500 values in between those ranges. X is equal to tf.cast x tf.float 32, we convert it to float, and then we have a function f lambda x. So what we are doing is we are uh, running those numbers through this function plus 0.6 to get a value, set of values. So if you look at f, if you look at the values of f, okay, that's just a lambda function. We'll use it now. Okay, so what we can do is plt.plot x tf.math.sigmoid x, and then plt.ylim minus 0.1 to 1 to 1.1. So that's the ylim, and plt.title sigmoid function. Okay, and now let's run this, and here is the sigmoid function we get, which is a nice curve that looks like an S, and hence the name sigmoid. So that's what we have. And let's now move on to the next step. So here we use the tf.math.sigmoid, and let's now move on to the next step, which is defining the log loss. So here we visualize the sigmoid function. I'm not sure why we wrote this line of code, which is the x lambda, this one. So if we comment that out and maybe delete f, so let's just say delete f, run that. So we deleted the f, commented that out, and run this again. And that will work just fine. Okay, I think that's just an equation that one could use for calculation. So we could instead of the value x, if we use the value of f instead and run this, the value so that's just a function, so that's not going to work. My apologies there. So yeah, let's leave it at that, and then we can delete this. Next we have the log loss function. So for log loss function, and for this we are going to define log underscore loss that takes in the predicted value and the actual value, true value, and computes the loss. So to compute the loss, we are going to abbreviate it as CE for cross entropy is equal to tf.nn.sigmoid underscore cross underscore entropy underscore width underscore logits, and labels is equal to y logits is equal to y underscore pred, and then we return tf dot reduce mean CE. So that's the function we have, which is the function that will compute the log loss values for us. And the next what we need is a rule to update the gradients. So the gradient descent update rule, and now we'll write code for that. Gradient descent update rule. And if you're not familiar with what gradient descent is, I'd suggest looking at the docs that are at the link above this in this notebook that I showed earlier, or you could look at the intermediate series as well. So we'll create a class logistic regression. This again takes in tf.Module, and as earlier we have init class first, init, and this init with two underscores, init underscore underscore self, that's one. And then we also have the next one, we have a callable call, and this takes in self. Okay, so let's leave it at that, callable, and then we are going to create so yeah, I think these are the two. So in the first case, what we are going to do is type self.built is equal to false, and then in here this takes in input self, x train is equal to true, and now what we are going to do is initialize the model parameters in the first call. So initialize the model parameters in the first call, and if not self, so if not self.built, then what we need to do is generate random values. So generate random values for weights and biases. So the W and B, so this is going to be our W, and biases, this is going to be our B. So random W, random underscore W is equal to tf.random.uniform shape is equal to x.shape and square brackets -1. Then we have comma 1, and this again will set the seed to 22. That's in the docs. So that's like that. And then for the next random value for the bias B, this is going to be called tf.random.uniform, and again shape open close is equal to open close square brackets, seed is equal to 22. That's just going to be a single value. Now up next we are going to define self.w is equal to tf.variable with a capital V random w, and then we are going to declare self defined self dot b is equal to tf.variable random underscore b. With these in place, we can now compute the model output, and so I'll say compute the model output, and we have z is equal to, so here's how we are going to, so first we need to multiply, so it's mx plus b. If we think about this as y is equal to mx plus b, the equation of the line. See, similar concept, except that here we are going to say this is the z and instead of M this is the W, and the B is our bias. So thinking about this, what we'll do is tf.matrix multiply x comma self.w, and then whatever value is the output of this, we are going to perform the addition tf.add, add this to the bias self.b, so self.bias, then put all of this inside of the z, and then we can squeeze that to remove any extra dimensions. sqee ze z axis is equal to 1, and if train, if that is true, then return z, else this is going to return tf.sigmoid of z, and tf.sigmoid is the function, indeed we used that earlier. tf.math.sigmoid is what we used. This is just using tf.sigmoid, and so that's the class we have created. So let's run that, and everything looks okay. Now we can validate. So validate to, or just we can say make check if it returns values in the range 0 to 1, right? So 0 to 1, if it returns the values in that range. For that we'll say log underscore regression, log reg is equal to logistic regression open close parenthesis, and then we are going to use y underscore pred is equal to log underscore reg x underscore train underscore norm, and we are going to take just the 5 values. So if we look at the 5 values down here, let's put them here. So these are the well, 5 columns, my mistake. So we have, this is 1, then we have the second one, this is 2, and then we have this 3, 4. Oh, wonder. So let's say we have, this is 5 by 3, so we have 5, 1, 1, 2, 3, 1, 2, 3, this is 4, and then the last one is 5, right? This is 5. Log reg x train norm, and then here we specify train is equal to false, and because we specified this as false, it's just going to return as the values that pass from the tf.sigmoid, and we can look at y underscore pred dot numpy. So numpy, and let's run this now, and hopefully, so these are the values we get, which are the values after they come out from this particular x train underscore norm, after they come out of this log reg, that is the logistic regression. And we see that the values are between 1 and 0. So this is 0.999 and this value is just 0.33. Now let's move on and look at the next steps. I'm going to delete this cell, and we are going to write 2 functions. One is to calculate the accuracy, and this function to calculate accuracy would use another function that will kind of look at, compare each value, predicted value, with a threshold to return another value that's either 1 or 0. So let's write that, create a heading here that says accuracy function, and for this we are going to first create a function predict underscore class y underscore pred threshold. This is threshold for logistic regression to classify if tumor is benign or malignant, we are setting this to 0.5. Again, this is arbitrary. Return tf.cast. What we are what we are going to return is this. We are going to compare y pred with the threshold. So if the values of this threshold, if the predicted values are greater than this, then this condition is going to be true and will return a value of 1. So let's say if our y pred that we have up above, if this value is 0.99, we check if it is greater than 0.5. Yes, it is, and so that's going to return a true. When we perform a tf.cast, my mistake, so we delete that cell. If we perform a tf.cast on this, so tf.cast without the d, and change this to data type that is tf.Float32, then as you can see, we get a value of, we should get a value of 1. That's right here. And if this value is less than the threshold, then we would get a value of 0. So essentially what this function is trying to do is converting the predicted values that we get into either zeros or ones, and that's all there is to this function. So we are going to do that and then put all of this inside of tf.cast, and then here we are going to specify the data type to which we would like to convert these to, and that's what we have, tf.cast right there. And in addition to this, we now define the accuracy function, and this takes in y underscore pred and y value, and y underscore pred is equal to tf.math.sigmoid y underscore pred. So the values coming out of the sigmoid function. Y underscore predicted class, the class is going to be the one that the function we just created returns class, and we input the values of y pred to that, and then we check equal. So we check if the values from this predicted values are equal to the actual values, and we are simply saying if the y predict class, if the predicted class is in fact equal to the y, right? If that's the case, and we are going to again cast this. So we are going to say tf.cast, and here again the data type will convert it to is float32. Right. So if it is the same, we'll get a value of 1. If it's not, we'll get a value of 0. And so if we calculate the accuracy value, tf.reduce underscore mean check underscore equal, and this thus we return the accuracy value, accuracy val, and that's the function we have created. Okay, so with all these all set up, we are now in a position to train the model. So let's create a heading, train the model, and for this there are a couple of things we need to do. The first thing we'll do is set the batch size. Batch size is equal to 64, and then the data set that we have, the train data, the X train, normalized X train, and Y train, which is right now, I think it's an eager tensor. So let's again look at the type X underscore train underscore norm. That is an eager tensor. We will convert. We'll use the tf.data sets again to convert this to using the from tensor underscore slices. So like this, we just say tf.data.dataset from underscore tensor underscore slices x underscore train underscore norm, and then we specify the y underscore train. So what we are doing is we are creating this we are combining the target and the features together and creating this using the tf.data.datasets and putting that in this variable train dataset. So now if you look at what the type is for this, uh, we can we can look at that print type train dataset, and let's look at why the error. tf.data.dataset from underscore dataset from tensor slices x train norm comma y train train dataset. Now let's look at what the error says. The truth value of an array is ambiguous, and oh right, so this has to be in a tuple, so I'm going to put another parenthesis there. Now if you look at the train dataset, we see that is a tensor slice dataset. What we do next is train underscore dataset is equal to train underscore dataset dot shuffle. We shuffle it buffer underscore size is equal to x underscore train dot shape 0. So that's the shuffle part. Then on this we are going to do a batch. So we say dot batch open close parenthesis batch underscore size. And now the type of batch underscore size is not found, so wonder why. Let's see, batch. So this is going to be shuffle name batch underscore size, because I haven't run this yet. So my mistake. So let's run these two. And we now have a batch dataset ready. Likewise, we can convert the test dataset that we have. So I'm going to simply change the name here to test, again change this to test, and change this to test, and again change this to test. The first one is going to be tf.dataset data.dataset.from tensor slices x test norm, and again instead of y train this is going to be y test, and then the x test we again are going to do the shuffle with the buffer size set to x test dot shape 0, and then we have the batch that is batch size. And when we run this, we should see that this is again a batch dataset as we had earlier. Now we are ready to write the training loop. So let's write that training loop. And in this training loop, we have like nested for loops. So the first will set the training parameters, set training parameters, and here we have epochs is equal to 200. So we set the epochs to 200. Learning rate is equal to 0.01. Then we have train underscore losses and test underscore losses initialized to empty lists with open close square brackets. Train underscore accuracies, test underscore accuracies, both initialized to empty lists that are open close square brackets. So that part is done. Next thing is creating the for loop. So this is the loop, training loop here. And so for epochs in range epochs, so for these number of epochs, there are two things we are going to do. First, we are going to work on the train set. So for x underscore batch, comma y underscore batch in train underscore data set. So that's one thing we are going to iterate over this, and after this we are going to do the exact same thing for the test dataset. So for x underscore batch, y underscore batch, and this is going to be in the test dataset. Two different things. And so to get started, I'm going to comment this out for now. And the first thing we have here is the batch losses. So batch underscore losses underscore train, then batch underscore accuracies underscore train is equal to empty list, so with the open close square brackets. And what we are trying to do here is collect the loss values and the accuracies for each batch as we iterate through this loop, and then in the end we'll put all of them together in that uh, complete train loss and test loss. Okay, so with that done, we can now uncomment this part and start working here. So here our main objective is to uh, get the gradients. So we'll say with tf dot gradient tape as tape, and if you're not sure what the gradient tape is doing, I'd suggest looking at the videos that discuss this in further detail. So essentially what we are doing here is think of gradient tape as a recording tape which records the values as we move in one direction, and then we use that recorded values in again when we go back to kind of update the values. So we say y underscore pred underscore batch is equal to log underscore reg x underscore batch, and so the predicted values for the batch, and then we calculate the loss for that batch is equal to log underscore loss y underscore pred underscore batch y underscore batch. So we have the actual values and the predicted values for that that batch, and we get the loss calculated. Now this loss we can use to calculate the accuracy. So batch underscore accuracy, uh, not really the loss, but we are going to use the actual and predicted values to calculate the accuracy. Accuracy in parenthesis y underscore pred underscore batch comma y underscore batch. We got the loss, we got the accuracy. So here we got the loss, we got the accuracy, and now the thing that we need to do is, so here is the batch accuracy. Okay. And what we are going to do next is update the parameters of the gradient. So update the parameters with respect to the gradient calculations, and this is how it would work. Grads is equal to tape dot gradient batch underscore loss log underscore reg dot variables, and for g comma v in zip gradients log underscore reg dot variables. Here we are going to say v dot assign sub learning underscore rate star g. So we are multiplying the values of g with learning rate, and then we are going to subtract those values. And next we keep track of bachelor training performance, batch level training performance, and here we say batch underscore losses underscore train dot append batch underscore loss. So the empty list that we created above, we're just putting these values in there, both for the loss values and the accuracy values. So batch underscore accuracy. So again, to go over this, just a quick recap of what we actually did. we started out with number of epoch. In each epoch, we take the trained data set and we work on in batches. So first we use the gradient.tape. We calculate the predicted value, then we calculate the loss, then we calculate the accuracy. Once we have calculated this, we use the gradient tape right here, tape.gradient, and input the values for the batch loss, and then we input the values for the log underscore regression, and that is then used to update the values here. So we subtract the values uh, by multiplying the learning rate with the G, and finally we uh, combine. We'll take these batch loss and the batch accuracy, missing the P there, and putting it in these empty lists that we have created up above here. So that's what we have for the training part. So this is iterate over training data. So let's create a loop here. So here we are iterating over the training data. So iterate over the training data, and likewise we are going to write the code to iterate over the test data. Right, that is here. Iterate over test data, and for this it's the same setup, except we do not have to calculate the gradients. Y underscore pred underscore batch is equal to log underscore reg x underscore batch, and then batch loss is equal to log loss y underscore pred underscore batch comma y underscore batch, and next we have batch underscore accuracy is equal to accuracy y underscore pred underscore batch comma y underscore batch. Okay, and again we can append all of these to the empty list we created above. So batch underscore losses dot append batch underscore loss. So that's the first, and then the second we have batch underscore accuracies underscore test dot append batch underscore accuracy. So that's now for the test data set part. So we are still in the same. We are still in this inner part of the outer for loop, and wonder why this is not, why this is highlighted in orange. Let's go back up and check if there are any typos. Log underscore, oh, so there's a typo here. This should be log underscore reg, not red. So that should fix that, but still wondering why we have this here, batch underscore losses. So batch underscore losses dot append. Oh, right, missing the underscore test there. Okay. Batch underscore losses underscore test, and then we have batch underscore ACS accuracies underscore test dot append. We go all the way up. Batch underscore, oh right, my mistake. So here this should be test, and then this should be test. Okay, so this should work now, and hopefully we got rid of the error. Let's see, we close that out, close that. Okay, so yes, so that did work. Next, what we need to do is once we have this, we need to calculate the what happens at each epoch. So epoch level performance, epoch level performance. That's what we are gonna calculate now. Train underscore loss, train underscore accuracy is equal to tf dot reduce underscore mean batch underscore losses underscore train, and then we have the next one, tf.reduce underscore mean batch underscore accuracies underscore train. And likewise for the test, we have test underscore loss comma test underscore accuracy is equal to tf.reduce underscore mean batch underscore losses underscore test, and then the next one is tf.reduce underscore mean batch underscore accuracies underscore test, and that's what we have for those two. Then train underscore losses dot append train underscore loss, then train underscore accuracies dot append train underscore accuracy, and likewise we have test, and then just everything for the test. I'm going to copy these and paste them right here. So this is for test. We have the test losses dot append, then we have the test accuracies dot append. So I wonder why this is showing an error. So let's go back up, and this is so test accuracies test losses, that looks okay. Let's go back down. Yeah, so that looks fine. So we have the train loss, train accuracy, test loss, test accuracies, and finally we have if epoch percentage 20 is equal to 0, then we are going to print, so every 20th epoch we are going to print this f epoch, and then the epoch that is the number of the epoch, comma training log loss, and here we have the train underscore loss and to 3 decimal places, and we put curly brace there, and then the quotation. So that's going to be the output of this particular entire for loop. So here's what we have. We started out with the epochs, and then we loop over the train dataset, then we loop over the test dataset, and we combine the information from all the epochs, and that's what we are going to print right here. So let's run this, and there's an error right at the here. Epoch, probably a typo that I have, and that's because this needs to be epoch and not an epochs with a plural. So hopefully this will work. And while this is running, okay, so we have the training loop, and the training loop did run, but we do not have anything in the output. Again, I'm wondering why that is the case. Let me check and come back. Okay, so here I went back and rerun this cell and then rerun this cell, and now this seems to be working. We have the log loss. The loss, it looks like it was decreasing, but then it again increased after a couple of epochs. So that's at least we have this setup now. Next, we'll look at the performance evaluation. So create a heading that says performance evaluation, and here we'll create the plots for the loss and accuracy over time. So the first one is for loss, plt.plot range epochs comma train underscore losses label is equal to training loss. That's the first one, and then I'm going to copy this first line and paste it down below, and that the second line would be for the test one. So paste this here, and this is again the range epochs. This is for test losses, and this we are going to call this as the testing loss. And after this we can assign these labels. So plt.x label, and here we have epoch, and similarly plt.y label, here we have log loss, and then we have plt.legend open close parenthesis and plt.title log loss versus training iterations. And when we run this, this is what we get in the output, and that doesn't look quite what I expected. Uh, so again, I'm gonna check what's going on here and then come back and rerun this. Right, I think I found the error. One issue was up here where we calculated the values for the norm. That's the class we created up here. Where is it? So let's scroll up here. So here this was minus like this. So this needs to be multiplication instead of minus. So that's one issue. And the next problem was here, after copy pasting, forgot to change this to test loss instead of the train loss. So this was a big mistake. This needs to be test. And now let's go up and restart and run all. So this is going to restart the runtime and run everything again. So hopefully now we should get these values that make more sense. And we should see the plot for the log loss versus training iterations shortly. And while that is running, why don't we copy this and paste that down here, where we are going to create another plot which is going to be for accuracy. And okay, so we need to create a bunch of cells, paste this here, and for accuracy, the instead of losses we are going to say accuracy is ACCS, and the same thing here, ACCS, and this is going to be training accuracy, and again this is going to be testing accuracy. And for y label we again have this as accuracy and with a percent sign on there. And finally down here we have accuracy versus training iterations. So while now again doesn't looks like it didn't make any difference, because we still are getting the same set of values, and that is what I need to figure out. Yep, so it's the same plot we have, so something is still missing. So let me go back and check again. Okay, finally figured out what the problem was. Here what we need is after this we not after this but up here after self.b we also need to specify self.built is equal to true, and this is what's going to enable the condition where the build has to be true. So after this first call, now if we restart the runtime and run all, then hopefully this should sort out the errors and we should get the output. I tried rerunning that, and that's what that output is. So let's run this again, and hopefully we should see the output shortly. And here it is. Yep. So this is starting out at loss of 0.6 and it will gradually go down and here it's going down to 0.08 and so on. And here we have a nice plot where the blue line is the training loss and the orange line is the test loss. And up here we have the same setup where the blue line is the training accuracy and the orange line is the testing accuracy. So that's how we can assess the model performance, and we can print. So print f final training log loss open curly braces train underscore losses -1 close square brackets colon dot 3f and closing curly braces. We copy this and then put this here. Final testing loss or testing log loss, and here we specify test losses and we have 3f. And now when we run this, we see that the training loss, final training loss is 0.8 and 0.08, and the final testing loss is 0.077. Likewise, here we can print the final training accuracy, and we can also print the testing accuracy. And here we need to change this to ACCS. Again, we change this to ACCS, and we get the training accuracy is 96%, 96.8, and the testing accuracy is better, 97.8%. Moving on, we can also look at confusion matrices, confusion matrix. And if you are not sure what confusion matrix is, I suggest checking out the videos in the intermediate series. What it tells is how good are the predictions. And for this, we'll create a function def show underscore confusion underscore matrix y. It takes in input arguments of y classes and typ, and here we have plt.figure fig size is equal to 10 by 10 and confusion is equal to sk matrix. So we are going to use the scikit-learn library to calculate, to get the confusion matrix, and this takes in y. The input has to be numpy array, and so therefore we are converting it to numpy, and y underscore classes dot numpy. Okay, and next we have confusion normalized is equal to confusion divided by confusion dot sum axis is equal to 1 and axis underscore labels is equal to range 2, axis is equal to sns.heatmap, and the heat map we have confusion underscore normalized comma x tick labels is equal to axis underscore labels, and let's bring that to a new line, and then below this we have y tick labels is equal to axis labels, and we have cmap is equal to blues, and annotation is equal to true, fmt is equal to 0.4f, so to 4 decimals, and square is equal to true. And finally below this we need the title and the labels again. So plt dot title confusion matrix and in the curly braces we have the typ plt.y label. Here we have the true label, and plt.x label we have a predicted label, and again there's a typo here, this should be label. And finally we can print. So let's run this. That's the function. You can now use this function to create the classes, but before we do that we need to get the predicted values. Y underscore pred underscore train comma y underscore pred underscore test is equal to log underscore reg x underscore train underscore norm comma train is equal to false, and log underscore reg x underscore test underscore norm train is equal to false, and train underscore classes test. So we are getting the actual and predicted classes. Test underscore classes is equal to predict class y underscore pred underscore train and predict class y underscore pred underscore test, and there is, this needs a t, and so those are the values. Now we can show the confusion matrix like so. Confusion matrix y underscore train underscore classes and training, and similar to this we'll have another one for testing. So copy that, put this here, and this is going to testing, and we'll change, instead of y train we are going to change this to y test, and this is going to be test classes. So the size of the figure, I'm going to change this to 5 by 5 instead of 10 by 10, and then run all of these again. And here is the confusion matrix we have. The reason why the typ did not work, because I had found the error, and that was because there was a missing f in front of these quotations. So now when we run these, we should have the confusion matrix with the training, and we have this for the test. You can see that out of we have the 0.9667 which were correctly predicted true for true class, and here we have 0.977. Now when we are looking at this, one thing we do need to know is what was the actual fraction of the malignant and benign. So if you look at the dataset.head, what we'll see is this is the column where we have the M and B. Let's check what is the proportion. Group by, we'll do a group by using the diagnosis column, and we can simply count the IDs that are there, that count, and let's just say reset underscore index. So we'll get a count. So these are the counts, and it's not a skewed data set. I mean, for both classes they are about this, not same, but they are at comparable number of. If it were such that 500 will belong to class B and just maybe 10 or 15 belong to class M, that would have been a skewed data set, and in that case then we would have had to think some more strategies to counter that. Right, so we have the confusion matrix, which looks good. The off diagonal elements are incorrect predictions. As we can see, they are much lower, and now we can think about saving the model. So save the model, and for this we will create another class, ExportModule. So let's do that. Class ExportModule, and this again takes in tf.Module, as the input, and first method is init as always, and self model norm underscore x class underscore pred, and inside of this we initialize the pre and post processing functions. So initialize pre and post processing functions. So self.model is equal to model, self.norm underscore x is equal to norm underscore x, and self.class underscore pred is equal to class underscore pred. That's the first one. And then the next we are going to write at the rate tf dot function input underscore signature. So that's signature is equal to tf dot tensor spec shape is equal to square brackets none comma none, and we do not need this quotation, so let me delete that and delete this quotation right there. tf dot function, we have this, and then the data type d type is equal to tf dot float 32, and float 32 like so. So d type is float 32, and this again you close this out with square bracket and the closing parenthesis there. So that's what we have there, and below that we are going to write. So below this we are going to define the call. See, def underscore call underscore self comma x. So self comma x, and here we are going to run the export module. So run the export module as in the same name we have. So export module for new data points, and I see that the screen is lagging right now, so I probably have to shut down the PC computer and restart it. Norm underscore x dot norm x, and y is equal to self dot model x comma train is equal to false, and y is equal to self dot class underscore pred y, and we return y from this. So that's the export module function we have created. Let's now initialize the class. Log underscore reg underscore export is equal to export module. Model is equal to log underscore reg. Norm underscore x is equal to norm underscore x, and we have class underscore predict. Pred is equal to predict underscore class. So with that initialized, we can now save the model. So here we say save model. Models is equal to temp file dot mkd temp, and save underscore path is equal to os dot path dot join. Here we have the models, models with an s. I'm going to put an s there, comma log underscore reg underscore export, and next we have tf dot saved underscore model dot save log underscore reg underscore export save underscore path. So that will save, and then we can load the model. So let's see what the error is. Model, that's my mistake. So there should be There shouldn't be an M there. There should be a comma, and that should work. Next, what we need to do is reload the model. Load underscore reg underscore loaded is equal to tf.Saved underscore model, then dot load save underscore path, save underscore path with the h, and below that we have test underscore preds is equal to log underscore reg underscore loaded, and here we have x underscore test with the s, and then we have test underscore preds. Look at the top first 10 records dot numpy, and this should be the, and let's see what the error is. Log underscore reg underscore loaded is not defined, and let's figure out a load. Oh, so that's my mistake again. This should be log underscore reg. So now this should work. Okay, so so this is now working, and here we have the predicted values. We could look at the actual values y underscore test and look at the 10 values, and here we have we can do a dot numpy on this and look at the array. So these are the actual values, and those are the predicted values, which look pretty good. So that's what we have in this video. I hope you got some intuition on how to write code for code for logistic regression from scratch using TensorFlow Core API. If you have any comments or suggestions, please do let me know in the comment section below. I hope to see you all in the next video. Thank you.